Okay, so let's get started. I hope that the test was all right. I think the poll suggested it's exactly split in half. Half the students said it was as expected, and other half said it was harder than expected. Okay, so we'll grade it and we'll see how it goes. All right. So a few other announcements. We have put up lab number 2. Okay, there is no rush. Okay, there's plenty of time. It's due at the end of the month. We're just giving it out well in advance so you can plan your spring break. You can plan the entire month and make sure that there is no last minute scramble. Right? Start early, finish early, and I think life will be good. If you start late, you may end up scrambling again at the last minute, like some of you had to for lab 1. Okay, so lab 2 is out. We'll also give a Docker lablet so you can get familiar with Docker. I'm going to cover it today, hopefully, because the second part of the lab requires you to use Docker and so on. All right. So what we'll do though is finish what we had started last time, which was virtualization and hardware virtualization. Okay, and then we are going to switch gears, talk about OS virtualization, Docker, and these types of topics today. Right. So this is the picture I had put up last time when we started talking about virtualization. This is about hardware virtualization and specifically full or native virtualization. Right. So there are two types of virtualization layers. They're both called hypervisors. One is called type 1. In type 1, the type 1 hypervisor is the OS. Okay, it's the thing that boots up. There is no other OS that runs on the machine when it boots up, that is. So it's going to boot, it's going to provide virtualization service, and it's going to provide an OS service for all the virtual machines that run on top of it. So it's a special type of an OS. Okay, you can't run general purpose applications on it. The only type of application you can run are virtual machines. Okay? So this figure shows two virtual machines. One is running Windows and applications on it, and the other one is running Linux and its application. Okay? That's type 1. Okay? Type 2 virtualization, you run on your standard laptops and desktops and things of that sort. Type 1 typically is run on servers. It's run in data centers and cloud platforms, not on desktop. Okay? If you want to use virtualization on desktops, you're going to use type 2. You will boot your normal OS, which we'll call the host operating system. Okay? Your type 2 hypervisor is actually an application that runs on top of your OS, like any other application. Okay? And then you basically use that hypervisor to create a virtual machine, and then inside that virtual machine, remember, the virtual machine is a software emulation of an entire machine like a PC. Okay? So inside each virtual machine, you can boot a normal OS, and then you can run your application. Okay? All right. So let me show you how this works, because you will have to do this soon. So you might as well, if you haven't done it before, know how it works. Okay, so I'm going to show you two examples of full virtualization. So here I have a type 2 hypervisor. Okay, it's called Parallels. The similar one called VMware Fusion. Doesn't matter which one you use. They both provide similar functionality. So in this type 2 hypervisor, so this is an application, right? So I'm still running Mac OS. This is an application that is running. It's an hypervisor application. I actually have 3 virtual machines in that hypervisor. They're all asleep at this point, so not started them. Okay, there are 2 Ubuntu and 1 FreeBSD. Okay, so, and they're all ARM virtual machines because this is doing native. It's ARM on ARM. The virtual machine is an ARM machine, and the native hardware, which is my Mac, is also an ARM machine. Okay, so you can start one of these. Okay, and let's hope it starts. Okay, so here we go. So it basically started, and now this is Ubuntu, right? So you can just see that you can just, I mean, it's like any other Ubuntu PC, just running inside a VM. Okay, so you can do this, and you will see that it's an ARM. You'll see here it says ARM64. Okay, so this is now running a Ubuntu virtual machine on my Mac. Okay, so you can have as many as you want, right? So you can start another one. I'm going to start this other one, the FreeBSD one. Okay, so here it now started, and now I have this is FreeBSD. So you can see that they're both running. Hold on. So I'm stuck in here. So this is running a all right. So you see that there are two virtual machines running here. One is Ubuntu OS, another one is a BSD OS on two virtual machines. Both of them are running on my Mac. Okay, this is a type 2 hypervisor. You can stop these virtual machines and they will essentially get suspended and go back to sleep. Okay, not something you can do on a I mean, you can't really suspend. You can in some cases, but typically you cannot suspend and resume like you can do with a virtual machine. Okay, so that's an example of native virtualization. I will show you a second example, which is going to be emulation. Okay, so this is a software, open source software called QMU. Okay, it can emulate all kinds of processors. Okay, so you can, there are 30 or 40 different types of hardware architectures it can emulate. So I have, in this case, I have a this is of course a Mac, and this is another application, another hypervisor. So I have a Intel. So you can see that this is a Debian or running on Intel. So it showed me the bootloader is going to boot. But it's going to be slow because it's doing emulation. It's running x86 instructions on an ARM processor. Okay, so every instruction is assembly instruction is being emulated. So you'll see that it's taking its own time to boot. It's going to take a while. Okay, and eventually it will boot, and then you will have another virtual machine. It's just slower. Emulation just tends to be slower than using native virtualization. So here we go. Remember my password will be logged in. So you see that now, I don't know if you can see this in the back, but if you actually do this, you will see that it tells you, I probably can't see it, but it says it's x86. So essentially this is emulating an x86 virtual machine, okay, which you can run on a standard machine. All right, so that was a very quick example of how hypervisors are going to work. I can shut that down. It doesn't slow down my machine. Okay, so it's gone back to sleep. So that's it. So that was a very quick demo of a type 2 hypervisor. Okay? So you can run this on your machine. You can run different operating systems and what. Yes, question. For the emulator, for the architecture same, the translation is faster. Yeah, so question is in the emulator, if you can do both of them the same way, will it be faster? So if you specify the same processor as the native processor, it is not going to do emulation. It's actually going to default to full virtualization. In fact, that same thing that I had a second virtual machine in there, that was an ARM. So if you run that, you can see that that runs much faster than the Intel because that's not doing emulation. Because there's no emulation, you're just using the same instruction. So you use native in that case. Okay, yes. Okay. Question is, why would we want to run in a virtual machine an OS that's the same as the underlying? Right. So if you just need access to a second machine for any reason, right? Let's say you want to do testing, right? You can say, I'm going to run in your lab 1. You could have run your client in one virtual machine and a server on your native machine. These are actually two separate machines. They're on the same physical machine, but you can do that. Or if you want to have a test environment to test your software, you can set it up separately from your main machine. So there are all kinds of reasons you want to use that. Of course, you can run a different OS. Right? So there's no reason to run the same OS. So this allows you to run Linux on the Mac. That's a good use case for it, right? You can run Windows on your Mac or Windows on Linux. So there are other operating systems you can run. That's a common use case as well. Okay, no question there.
OS gets affected by some malware.
Okay, question is, if the guest OS gets affected by malware, will my host OS also get affected by malware? So the guest OS is its own operating system. It's a real OS that is running, right? So if it gets impacted by any security attack, that machine is breached. But the host OS is a separate operating system altogether, right? So that is not going to be impacted. All right. Okay. So that's a quick example. Now, if you had done this on type 1 hypervisor, it would look the same, except that we wouldn't be running on something like a Mac because there is no underlying host operating system. What you are going to boot on your machine is the hypervisor. So you'll just get a command line prompt and you can start creating or starting VMs and things like that. Other than that, it's the same, right? Okay. So with that quick, your question, yes. The question is, why do we want to use the type 1 hypervisor? Why can't we install the OS? This allows you to run multiple virtual machines on one server. And if you have a large server, you want to make smaller servers and run different operating systems and different applications, you would use virtualization. If you just wanted to run one OS, then you shouldn't use virtualization. You can just boot the OS, then you don't need it, right? Okay. Yes.
Do data centers use the type 1 hypervisor?
Okay. Question is, do data centers use type 1 hypervisors? So type 1 hypervisors are used in all data centers, all cloud platforms. When you actually go to a cloud platform and ask for a machine, you are actually getting a virtual machine, right? And that physical server might run lots of other virtual machines that have been given to other customers. You are not getting a physical machine. You actually get a virtual machine. So virtualization and type 1 hypervisors are very common in data centers and also in cloud platforms. Okay. Yes, question. Yeah, question is, can one virtual machine span multiple physical servers? That's your question, right? So typically you will not do that because the hypervisor runs on one machine, right? You can slice that machine into smaller components, but you can't make one OS run on multiple machines. Then you have to get two virtual machines and make them talk to one another using any distributed system, right? So then it looks like a distributed system. Yes. Can the operating systems communicate with each other through the hypervisor? You mean to say there are two operating systems that are running here, can they communicate, right? So as far as the operating systems are concerned, they don't actually know they're running inside a virtual machine. It just looks like a physical machine with a network card, with an IP address, right? So just like saying, if I ran these two operating systems on two PCs, can they communicate? If they know each other's IP address, they can, of course, communicate. The same would be true here, right? So it looks exactly the same and in fact works the same way. Right? Each of them will have their own IP addresses. They'll see a separate network card and all of that. Yes. Okay. Question is, if these two systems want to communicate, what would they use? Shared memory or TCP/IP? So as I said, each machine is a separate software implementation of a full PC, right? You can't have shared memory across PCs, right? So this is going to, as far as these OSs are concerned, each of them is running on a virtual machine that just looks like a complete PC. There's no concept of working with another PC using shared memory, although they actually run on one physical server, right? So they have to use networking mechanisms like TCP/IP, just as you run any two machines. Right? So no different. Just so happens that they're running on one. Okay. Okay. So let's now talk a little bit about how all of this actually works. How do hypervisors work with operating systems that are running inside them? Okay? This is going to require a little bit of understanding of architecture concepts, okay? Undergrad level architecture. Okay, the only real concept you need to know, there are two. One is any processor, any hardware processor actually executes in at least two modes, something called the user mode and something called the kernel mode. Okay? In user mode, when user applications run, they run in the processor is then running in the user mode. Okay? When the OS kernel runs, it runs in the kernel mode. Okay? So you may say, what's the difference between a user mode and the kernel mode? Okay? The main difference is in kernel mode, all assembly instructions that the processor supports are allowed. Okay? In user mode, certain instructions are disallowed. Okay? Specifically, any instruction, okay, that is going to make sensitive changes, like it basically does I/O, it changes memory settings, okay, or it halts the processor. These are all sensitive instructions. We only trust the OS to perform those instructions. We do not let user programs go and start mucking around with memory, because then they can get access to some other processor's memory, or go and halt the processor and just shut down the machine, or any of these. Right? So whenever you design a processor, you take certain instructions and you only allow those instructions to be executed when the CPU is running in kernel mode. Okay, and the CPU runs in kernel mode whenever the kernel is executing on the CPU. Otherwise, it runs in user mode. Okay, very basic architecture concept, that something you should know. Okay, so that's one. Okay, and so the other thing you need to know is there are essentially standard instructions that any process can execute, whether it's the OS or the user application. And there are certain instructions that only the kernel can execute, specifically when executing in kernel mode, and we will call them as sensitive instructions because they're sensitive. We don't trust user applications to execute them. Okay? And then there is another group of instructions which we will call privileged instructions, and these are instructions that are going to cause a trap for one reason or the other. Okay? So a trap is an interrupt. Okay? When you execute the instruction executes, but it also creates an interrupt. Okay? So any instruction that creates an interrupt when it executes is called a privileged instruction. Okay? Now we have the result that was proved in the 1970s was type 1 virtualization is only going to work on processors where the sensitive instructions are a subset of the privilege instruction. In other words, type 1 hypervisors can only work on a processor where your sensitive instructions also generate interrupts. Okay? So if you don't have that property, the sensitive instruction just executes but does not trigger an interrupt, then you cannot run a type 1 hypervisor on that machine. Okay? Now the question is, why is this property true, or why does this even make any sense? Okay? So let's try to understand what is actually happening when we have type 1 hypervisors. Okay, this is only true for type 1, not required for type 2. Okay, so what did I say in type 1 hypervisor? This is the picture. Okay, what is booting on the machine? What's running on bare metal? It's the hypervisor. So the hypervisor is the OS. Okay, is the hypervisor that's going to run in kernel mode. Okay, so everything else runs in user mode. Okay, so now we have Windows, okay, which is running in its own virtual machine. As far as the hypervisor is concerned, that's a user process. Okay, so now we have Windows that's running in user mode. Okay, is no longer running in kernel mode because that's not the real OS at all on this machine. The real OS is the hypervisor. That's the only thing that runs in kernel mode. Okay, so Windows running in user mode. Okay, but Windows does not know this. Windows thinks it's running on an actual PC. Okay, just so happens it's a virtual machine, not a physical machine. Okay, so Windows will think that it is the operating system. Hence, it will try to execute sensitive instruction. It will try to do I/O. It will try to do memory map changes and things of that sort. Okay. Now, what did I say earlier? What happens in user mode? You cannot execute sensitive instructions, right? Because that's just not allowed. Windows does not know that because it thinks it is the OS, so it can do whatever it wants. So it is going to execute privilege instruction. So what is going to happen when you execute privilege instruction in user mode? Okay. It's going to give you an error because that's disallowed by the processor. Okay. Because only the kernel can execute these instructions, and in which case only the hypervisor can execute these instructions. Okay. So Windows tries to do something sensitive. Okay. Because it is not running in kernel mode, it is going to get an error, specifically that instruction will trigger a trap. It will generate an interrupt. Okay, what does an interrupt do? Yes, alerts the CPU. Specifically, it alerts the kernel. Okay, that interrupt is always handled by an interrupt service routine because interrupts are handled by the operating system. Okay, so whenever that Windows OS there is going to try to do something sensitive, it is because it's in user mode, generates a trap. The trap causes the hypervisor to run. So the hypervisor is going to figure out that an operating system inside a virtual machine is trying to do something sensitive, okay, but it's not allowed to do it. Okay, so then what is it going to do? Okay, it needs to perform that task on behalf of the operating system. Okay, so it will then make whatever that Windows OS wanted to do, it is going to perform on its behalf. Okay, and then it will return back to Windows. Okay, so Windows will not know that this happened because it's all happening underneath. It tries to do something sensitive, you're trapped to the hypervisor. The hypervisor says, I'm going to do it for you. It will perform those operations, go back to Windows. Windows continues executing. Okay, so in this case, Windows can still continue to do sensitive things. It's just that it has to depend on the hypervisor to perform them for it, because it is running in user mode. It is not allowed to perform those operations directly. Okay, on a normal hardware, this would not be the case because it is the kernel. It will run in kernel mode, so it can directly perform those instructions. But in this case, you have to have this one level of indirection for things to work. Okay, because Windows is no longer running as a trusted entity; it's running in user. Okay, is that clear? Now, if all of that has to happen, okay, you have to understand that every sensitive instruction has to perform a trap. Otherwise, this will not work. Okay, and specifically, all early Intel processors essentially did not have this property. They simply ignored sensitive instruction that ran in user mode. Right? You are a user process, you try to do something that's sensitive, the processor will simply ignore it, saying this is in user mode, you cannot execute it. I'm not going to generate an error or create an interrupt. I'm just going to ignore this instruction. Okay? So what that meant is early versions of all Intel processors did not have support for type 1 virtualization, because type 1 virtualization depends on this property. Okay? So in other words, early processors, specifically Intel processors, could not run type 1 virtualization. Later on, of course, all Intel processors and AMD processors fixed this problem. Okay? And they have now something called VT in Intel, that's called virtualization technology. AMD has something called SVM. Yeah, I think it's something virtual machine, forget what S means. But both of these technologies, what they allow you to do is they allow you to selectively turn on interrupts for certain instructions using a bitmap. Okay, so when you turn on VT, it will say, here are instructions that should trigger a trap. Okay, so it will enable the property that we want, okay, on the fly. If you turn it off, then it will look like an old style processor where you are ignoring all of this all of the sensitive instructions in user mode. Okay, so by adding this new feature, now Intel processors can support type 1 virtualization. Okay, so it should be clear why you need this property in the first place, and why, if you don't have that property, you cannot actually run any type 1 hypervisor. You can do type 2, but not type 1. Yes, question. Are there instructions that are privileged but not sensitive? Yes, you can have instructions that are privileged but not sensitive. You can do a divide by 0. You can just write a program that divides by 0. That's going to give you an interrupt. Right? So you can do things like that. You can have pointers that try to access some location that don't belong to you. Okay, that will also generate a trap. In all of these cases, your process might crash. Okay, or you will actually get an exception that you have to handle. One of those two things have to happen. Yes. Yes. Yeah. Question is why do type 1 hypervisor not require this property? Okay. I will explain that in a moment. Okay. We haven't gotten to type 2 yet. All right. So here's a picture that shows what I just showed you. Okay. So here is a hardware. Okay, that's gray box. Type 1 hypervisor is running on hardware. So it's running on bare metal. It is the OS, okay, for this machine. Okay. That's the thing that runs in kernel mode. Okay. You have one virtual machine. Okay, that's your guest, and it's running a guest operating system. That's not running in kernel. The guest operating system, as far as the hypervisor is concerned, is a simple application. Just runs like any other user process. No privileges at all. Okay? So now whenever that OS is going to perform a sensitive instruction, you'll see that it's going to create a trap because that was executed in user mode. The trap causes the hypervisor to run. The hypervisor catches that interrupt, processes it for the OS, and then you go back to the OS, and the OS assumes that the instruction just got executed. Okay, so they are basically a little bit extra work to do whenever you have sensitive instructions executing inside guest operating systems. Is this clear? Okay. So now let's talk about some examples, and I'm going to show you type 2 hypervisors, and we'll see how they work. Okay. So here are two real type 1 hypervisors. Okay. This one is a VMware's ESXi product, which is a type 1 hypervisor. Okay, that's very popular, widely used in all data centers. And you can see in this case, a simple example, you have a server hardware, you have the hypervisor, it's running 3 VMs. It's running 2 Linux operating system VMs and 1 Windows VM. You can create as many as you want. And you are only limited by how many cores, how much RAM that server actually has. Okay, so that's one. Okay? And then you are in the world of Windows, where Windows has a hypervisor, which we call Hyper-V. Okay? That is Windows virtualization technology. Okay, when you turn on Hyper-V, it runs on Windows Server. I don't think it's supported on desktop versions of Windows. Okay, so if you have the server version of Windows, it will come with Hyper-V. So you will actually boot Hyper-V, which is basically Windows with Hyper-V turned on. And then it allows you to create what are called partitions, which are essentially virtual machines. So you have a parent partition. Okay, that is where your device drivers run. That's where standard Windows run. But you can essentially see, you can create multiple child partitions. So here you have in a child partition, your second Windows running. So Windows is running on Windows. You can do that, of course. You can create a VM and boot Windows in it as a second guest operating system. Or second Windows is a guest operating system as opposed to the native one that was booted on. And you can create many of these. Okay, so you can do exactly in the same thing in the Windows world, where you have a type 1 hypervisor, which is Hyper-V. Okay, that's the Windows version of hypervisor, and create partitions, okay, which are VMs in this case. Okay, yes. Can you repeat what the question is? Yeah. Yeah. Okay. So there is a question here about this hypervisor runs in ring -1, kernel mode runs in ring 0. There is no real ring -1 on a processor. Okay. It is just to show that it has a little more privilege than the rest of this. All of this is actually Windows itself. Okay, because Hyper-V is inside Windows, but from a conceptual standpoint, this has a little more privilege than what runs on it, but effectively it's the same thing. There is no negative privileges on processors, okay, but that's a conceptual view. Yes. Can a physical machine run more than one ESXi host? A physical machine can boot only one thing at a time, right? So you will boot one OS, whatever that is, the standard OS, or you will boot hypervisor OS. Okay, so you can only have one of these running, okay, because that's what is booting when you power it on. So you can't boot two things at the same time unless you have other kinds of hardware partitioning, but normal machines will not support that. Okay, all right. So here are two more examples, which I'm going to go through quickly. Then we'll go and look at type 2 hypervisor. That is how type 1 hypervisor works in the Linux world. It's called KVM, or kernel virtual machine. Okay. Now, in the Linux world, you don't actually have KVM booting on the machine. Linux itself boots on the machine. Okay. So Linux is acting both as an operating system and a hypervisor at the same time, because it has a KVM module loaded in it. Okay, this is Linux. Okay, so when you want to do type 1 virtualization on Linux, you can actually boot Linux itself. Okay, and you just turn on KVM, in which case it starts supporting KVM virtual machines. But you can also run applications on Linux because it's still standard Linux. So this hybrid kind of scenario where the hypervisor is a general purpose operating system, but it also has type 1 hypervisor capabilities. Okay, so that's your KVM world, and then you can actually have libraries, and you see that QMO is running on top of that, that allows KVM VMs to do emulation. It can do native virtualization. All kinds of things can be done. Yes, question. Question is, if you boot Linux and you run a virtual machine in it, does that not make it type 2? It is a little bit of a question as to whether you want to call it type 2 or type 1, because you still have the hypervisor running inside the OS. Okay? We call it type 1. In standard type 2 hypervisor, type 2 virtualization, the hypervisor is going to run as a standard application. Okay? As I showed you here, okay, that the VMware or Parallels, they run as application. Here the hypervisor is still inside the OS, which is why it's considered type 1. Okay, yes.
Whenever you're booting a guest OS on this OS, you start in first then
The question is, how will you start a virtual machine? In this case, will you boot the always? Okay, you have to boot something. Okay, you boot in type 1, you boot the type 1 hypervisor. In this case, it just happens to be a Linux with a type 1 hypervisor inside it. That's KVM. So you will boot standard Linux, okay, and then you will essentially start kernel virtual machines, KVMs, and then you will run another OS inside. Okay, so there are other examples. There's one for Chrome, which I'm going to just ignore here, but you get the basic idea of what type 1 virtualization does. Okay, so let's talk about type 2 virtualization. Okay, there are many examples, and I showed you 2 examples. Okay, the demo I showed you was all type 2 virtualization. Okay, now type 2 virtualization no longer requires the property where your sensitive instructions have to generate a trap. Okay, so you may say, how does it work in that case? Okay, you will still run a guest operating system inside the VM. The guest operating system still thinks it is the real kernel. It will still perform sensitive operations. Okay, how are you going to handle them? Okay, so here is how type 2 hypervisors work. So in the type 2 hypervisor, okay, as the kernel is executing, okay, the type 2 hypervisor actually scans its instructions. Okay, if it encounters a sensitive instruction is about to be executed, it is going to on the fly, okay, replace that instruction with a function call. Okay, so this is all happening while the OS is executing. Right, so you have guest operating system. Let's say Windows is executing on a type 2 hypervisor. Okay, as instructions are being executed by Windows, your hypervisor is scanning all the instructions that are about to be executed. If you see a sensitive instruction, okay, you cannot execute it, right, because you will just get ignored. Right, you will go and replace that with a function call. Okay, so when the OS actually executes that instruction, it's going to execute that function call instead. And what does this function call do? Okay, it is going to go and invoke the hypervisor. There's a function call that says go invoke the hypervisor, and the hypervisor is essentially going to perform those operations. Okay, so it's just like a system call. It's now a call that is going to a hypervisor. Okay, because you're doing this on the fly, right? You don't need to have a property where those sensitive instructions cause a trap, because you are actively looking for those instructions and you are replacing them on the fly. There's a binary translation on the fly, and you are rewriting the code on the fly as well. Okay, so essentially sensitive instructions are replaced by procedures that emulate them. Okay, that effectively become function call that call the type 2 hypervisor. And the type 2 hypervisor is also an application. Remember, it cannot also perform that sensitive instruction. So it will actually make a system call to the underlying OS, and the OS is going to perform those instructions. Okay, is that clear? Yes, question. So the question is, there are some applications that cannot run inside a VM. How do they know? So, I mean, you can know what your architecture or you're running on. Okay. Now, I don't know if the applications you are referring to do not run because they are not licensed to run, or there is something that preventing them from running. Right? Sorry, could you say? I didn't understand what you anti-cheat software. Okay. So I think that there is fundamentally no reason why something cannot run inside a virtual machine, but it just looks like a physical PC. Okay. But in some cases, you are not going to let something run to prevent bad things from happening, or you just don't license it. So for example, Mac was not licensed. Mac OS was not licensed to run inside virtual machine. If you try to boot an early version of OS X in a VM, it would just complain saying cannot run. Okay? And in this case, I think it is basically disabled from running. There is no technical reason the code will not run. Okay? You just say that this is not allowed, and so you just prevent it from running. How do they find out that they are on a VM? That I'm not sure. I think there's a way to query and figure out what processor you're running and probably figure that out. Okay? Yes, question.
Usually there are markers.
Yes. Yeah. Yes. So that is just a mnemonic which say, if I see this driver, I know that this driver is used by VirtualBox or VMware, but you could change it. Then I don't think you can prevent it from running. I mean, if you're just looking for some strings. Yeah. So, but there is no real reason that something can, if a OS can run, an application can run as well. Okay. Some things you may not be able to do, like take full advantage of graphics card and things like that. Other than that, you should be fine. Okay, question is, what happens if the OS has certain hardware requirements that either the physical machine or the virtual machine does not satisfy? So that can very well happen. You might have OSs that say it needs at least 16 GB of RAM. If you create a VM with 4 GB and try to boot it, it will just not boot, but it will just look like you're booting it on a physical PC without the right hardware. Right? So it's no different from saying, if I had a physical machine that did not have that hardware, what would happen? The OS probably wouldn't boot. The same thing will happen in a virtual machine. And if you give it less resources or the wrong type of resources, it will not run. Okay, all right. So that's type 2 hypervisors. Okay, there's a third way of doing this. It's called para-virtualization. In para-virtualization, you actually don't run an unmodified guest operating system. Instead, you run a modified version of the guest operating system. Okay. But everything else is the same. You still have a type 1 hypervisor, but rather than running an unmodified OS, you run a modified version of the OS. So you will say, what does this modification do? Okay. So what you have effectively done is, you as a programmer have gone and looked at the kernel, okay, all the code in the kernel, and everywhere there is a sensitive instruction being called, you just replace it by a hypercall. Okay. So when this modified OS runs, okay, all of your sensitive instructions are gone because you removed them. You created a modified version of the OS where every sensitive instruction has already been replaced with a function call that invokes the hypervisor. This modified OS only runs on this hypervisor. It doesn't boot anymore on normal hardware because you went and replaced all those sensitive instructions with a call to the hypervisor. Okay. Now, if you have this type of modification, you can imagine that this is still going to run on any processor. Okay. You eliminated the requirement that sensitive instructions have to cause a trap. Okay. Because you removed them from the guest operating system. There are no sensitive instructions. You replace them with function calls. The function calls invoke the hypervisor and make the hypervisor do the work for you. Is that clear? Okay. So you have done effectively for a type 1 hypervisor what the type 2 hypervisor was doing on the fly. Okay. In type 2 hypervisor, the hypervisor was scanning the code and replacing every sensitive instruction with the function call on the fly. Okay. In para-virtualization, Some human did this once by scanning all the code and replacing all sensitive instruction with that function call, and you compile that kernel. So now you don't no longer have to do it at runtime, and nor do you now have a requirement that the sensitive instructions have to cause a trap. So in a para-virtualized environment, you can run a type 1 hypervisor on older processors. In fact, it is the only way to run type 1 hypervisor on older processors. But it requires that you have to modify the OS, okay? Which also means that you have to access to the code of the OS. You could not do this on Windows because Windows is not open source, and only Microsoft will be able to create a para-virtualization. But you could do this for any open source OS. Right? So in fact, there are para-virtualized versions of Linux and FreeBSDs that did exactly that. Okay? That is how you could do type 1 in old days before the processors added support for it. Okay? Any questions? Yes. So you're asking a type 2 hypervisor, if you make a sensitive instruction get replaced with the procedure and you call the type 2 hypervisor, well, the hypervisor eventually make a call to the actual guest host operating system, right? Yes, so you don't need to trap to the host operating system. Any user process can always invoke the operating system through a system call. System calls are ways by which you invoke OS service, right? So if a user process wants to do something privileged, you always use a system call to make the OS do it for you. So in this case, your type 2 hypervisor will use system calls to just ask the OS to perform some operations, allocate more memory, read some file. All of these are privileged operations, right? So you can make the OS, the guest OS, the host OS perform that operation for you just through system call interface. Okay, question is, what is the difference between a system call and a trap? A trap is like an interrupt. Okay, when an interrupt is raised, okay, essentially you are going to trap into the OS. The OS will run. It will see what caused the interrupt and service it. Typically, you will do this for hardware interrupts. Will be a packet has arrived on my Ethernet card, or the disk has finished its I/O. So go take the data it read. So these are all hardware interrupts. Okay, so you can also use the same concept in software and generate software interrupt. Okay, so interrupts are very different from system calls. The system calls are actual functions with methods, right? It's like an actual function call. The interrupts are a different mechanism for invoking the kernel and having it do some work for it. Somebody had some question here. Okay. All right. So that's para-virtualization. Here's an example of a para-virtualized hypervisor. It was called Zen. Okay. There's a nice paper that goes with it that I'm going to make available. So you will see that essentially that is your that's hardware. The layer above it is type 1 hypervisor. Okay, that's a Zen hypervisor. Okay, and this can only run a modified version of Linux. Zen is so Zen supports para-virtualized operating system. Specifically, it runs essentially modified version of Linux, and there's a modified version of BSD as well, as you can see. Okay. Now, the interesting thing about Zen was it also constructed what was called domain zero virtual machine or a control virtual machine. Okay. So all the drivers for the OS were essentially put in one virtual machine. Okay. If some other virtual machine wanted to make a driver call, it would effectively send that request to the domain zero virtual machine, and then that would invoke the hypervisor and make that. Okay. So they call it the driver domain. So they put all the drivers in one virtual machine with increased safety and things of that. So yes, question. The question is, wouldn't this require communication between operating systems? So these operating systems will communicate through the hypervisor, and they will invoke driver calls and things of that. So yes, they would. In fact, you can have virtual machines communicate with one another. They are all network machines. Right? So in this case, you don't need to necessarily use the network, but you can use other mechanisms to communicate. Okay, you can make a call to the hypervisor and have it talk to the driver and things of that. Okay? But yes, you do need IPC for sure, inter-process communication. Yeah. Okay, question is, what does para-virtualization refer to? Is it the modified OS? Is it the hypervisor? It's some combination of the two. Para-virtualization is an approach. Okay, the approach says you want to use type 1 virtualization and you want to run operating system kernels on top of that without actually having it use the trap mechanism of a standard type 1 hypervisor. Okay, so that approach is called para-virtualization. Okay, now you will run, when you have para-virtualization, you will have a type 1 hypervisor that supports para-virtualization. What does that mean? It has to export a set of calls that the OS can invoke. Those are called hypercalls. OS has system calls. Okay? Hypervisors have hypercall. So a para-virtualization layer will have hypercalls that it exposes. And then the para-virtualized kernel has to replace every sensitive instruction with a equivalent hypercall that asks the virtualization layer, which is the type 1 hypervisor, to make that to perform that operation. Right? Yeah. So the question is, will you get faster execution at the cost of having modified operating system? So you will execute faster than type 2 for sure, because you are not scanning code and changing code on the fly. That will slow you down. Okay, this is going to run at native speed because it is not doing any of that extra work. But the cost you pay is you will only require, or it will only execute modified operating systems that use hypercalls. Okay, all right. So that is Zen hypervisor. Let's go quickly talk about virtualizing some other resources. I won't spend too much time on this because virtualizing the CPU with all this extra instructions and traps is really where a lot of the virtualization work goes in. But you do have to virtualize all resources. You have to virtualize the disk, you have to virtualize the network card, you have to virtualize memory, and so on. Okay, so I'm going to give you very quick snippets of how it is done, but we won't go into all the details like we did for the processor. Okay, so let's talk about memory. Okay, so the operating system is responsible for managing the RAM on the machine. Okay, it is responsible for deciding how much memory to allocate to a process, specifically which pages in that RAM get allocated to which process, or how to maintain the page table, and so on. These are all basic ways you are going to do memory management. Okay? And an OS is responsible for doing this. And all of these memory management instructions are sensitive instructions. So you cannot let a process go and change its page table. Then it can basically go and access anything it wants. Right? So only the OS can do this. But as I said, in this case, a guest operating system is not allowed to do this. Okay? So the way you are going to do this is your hypervisor is going to maintain a second page table for every page table that the OS has, which we'll call a shadow page table. Okay? The shadow page, so whenever the OS wants to make some change, okay, it will cause a trap because it's going to execute some sensitive instruction. You come to the hypervisor, the hypervisor makes that change in the shadow page table, which is then reflected back to the OS. Okay? So the OS essentially sees the change made by the hypervisor on its behalf. Okay, in a what is called a shadow data structure, which is effectively mirroring the actual data structure. Okay? So that's the trick that virtual machine designers have used to virtualize memory. You essentially have the hypervisor do all of the work for you through shadow mechanism, because basically gets reflected back to the OS. Okay? That's one example of how you're going to virtualize another resource. The second example is virtualizing disks. Right? So you have a disk on your machine. That's where all the files are stored. Okay? Now, your guest operating system also thinks it manages a disk. Okay? But the real disk is managed by either a host operating system or it's managed by the type 1 hypervisor, not by anything that is going to run inside a virtual machine. Okay? So then how are we going to expose this concept of a disk to a virtual machine? Okay? So we are going to essentially use the concept of a virtual disk. Okay? A virtual disk for all practical purposes, is going to act like a physical disk to the OS. Okay? But on the actual disk, the virtual disk is simply a file. It's a large file. Okay? That file essentially stores all of the data for that operating system. It will store all the files that Windows has. Any user programs are stored in it. Anything else that the user creates are stored in it, and so on. Okay? So the way you will actually do this is you will create a giant file on your machine. Okay? And that file is actually going to act as a disk to the guest operating system. Okay? Whenever the guest operating system tries to read or write to a disk, okay, the underlying hypervisor is going to read and write from this file and provide the data. All the data that you would store on an actual disk is now instead stored in a file. Okay? The file just pretends to be a disk to the operating system. Okay? And you should know this because when you are going to start using virtual machines in the future labs or lablets, you will have to create a virtual machine disk image. Okay? As going to be a large image that you will see on your machine. Okay? What it is basically the disk for the virtual machine. Okay? And all the OS that you install will actually be stored in that one file. Okay? That one file acts as an entire file system to the OS. Okay? All the data is stored outside. It just looks like a file. You can't peek inside it to see what is in it unless you know how to look at a file system. Okay? So, but as far as the OS is concerned, it can boot from that file. It can read or write to that file as if it's reading or writing to it. Okay? That is the concept of a virtual disk. Okay? That's how you are going to virtualize I/O. Okay? And so you will see that there are things called VMDK files in VMware. If you use the VMware type of hypervisor, you will create a VMDK file. Okay? That's your virtual disk file, virtual machine disk file. Okay? Or you will have some other name that basically is going to act as if it's a large disk. Okay? And you can do the same thing for networking, where the network card is also emulated. Okay? So you'll have logical network cards. Okay? And then when you try to send packets to it, they'll actually be sent to the physical network card because that's how communication has to happen. Right? Yes, your question. Yeah. The question is, since there are, I said, a virtual disk is basically a file. Okay, what is the mapping? Is there one virtual disk for every virtual machine, or can one virtual disk be shared? That's your question, right? So one virtual disk acts as a disk. Okay, so you're going to dedicate it for one virtual machine. So then if you want to create a second virtual machine, okay, that OS will have its own disk. You can't have two operating systems running at the same time sharing one disk, and they will overwrite one another. Right? So you create one disk for one machine. Okay? Then you allocate all the files or store all the files inside that virtual disk. Okay? And network virtualization is the same thing. Okay? You are essentially going to take a Ethernet card. You can do emulation of that card. So it's a software emulation. But when you read or write to that network card, okay, you are essentially going to create traps and actually copy the packet into the physical network card and actually send it out. Okay? So the logical network card cannot communicate. It's really a software implementation. So to perform actual communication, you still need a real network card to send, because your virtual machine can communicate with other machines on the internet, like any other machine. Right? So you'll map the logical network cards to a physical network card, and when packets arrive, basically the physical network card will deliver it to the application, which in this case is the OS, and then the OS will take it from the network card and do whatever it needs to do. Okay? Yes, question. Yeah, so question is, in shadow page table, are you going to map the guest physical address to host physical? Is that what you said? So essentially, you are going to have your own address space inside a virtual machine. The virtual machine is given some amount of RAM. That's a subset of the RAM on the physical machine. So when you create a VM, you say create this VM with 4 GB of RAM. Okay, your machine might have 16 or more. Right? So you have your own memory map. Okay? And so your page tables inside that OS will refer to the memory allocated to that OS. Okay. Now that memory map will translate to some other physical memory address. Okay. And that page table is going to keep all that mapping for you, right? Because address 10 inside a virtual machine might be completely different physical address on the real machine. A guest will have a virtual to physical, but that physical is still a virtual address in there. So there has to be another mapping that will be done in the shadow page. Yes.
There is one shadow page table per VM.
Well, technically, there's one page table per process data structure. So every process has one, right? So you will have to keep a whole bunch of them inside each VM and then do extra mappings. Okay. This question. Yeah, so that's a good question. The question is, basic question is, can type 2 hypervisors also take advantage of VT technology, which was designed for type 1 hypervisor? Okay? So there are all kinds of, there's a good question. There are all kinds of hybrid implementations to speed up type 2 virtualization, right? So the default case is you don't require VT, you're just going to sit and scan instructions and replace them. But if the processor supports it, why not take advantage of it? So rather than scanning it, you may as well let the instruction execute, cause a trap, and then perform whatever, do whatever type on it. So there are some implementations that have started doing exactly that, right? So they can, and you don't need to scan and replace. You are essentially going to use trap and execute, okay, as an alternative mechanism. That goes away from the original design, because the original design said you don't need any hardware support. But now if you have hardware support, you take advantage. Anything else? Okay. All right. So I think we are done with this. We're going to move on to OS virtualization. Okay. So in whatever time is left, which is not a whole lot, I'll introduce this notion of OS virtualization, which is the basis for things like Docker. Okay. So what we talked about so far is full virtualization. Right. So type 1 hypervisor, type 2 they are virtualizing the processor, they're virtualizing all the hardware resources and so on. Okay. Now we are going to go one level up and talk about doing this at the OS level. So we are using now the native interface of the OS, which is a system call interface, and expose another interface, okay, which is what OS virtualization is. Remember, virtualization takes one interface and uses it to emulate a second interface. Okay. So here we'll take one OS interface and emulate another OS interface, which is often the same one, okay, which will allow us to create lightweight virtual machines, as we'll see. Okay. So essentially, your one OS interface can be used to emulate a second OS interface. So in some cases, this is useful for backward compatibility, okay, because system calls also change over time. A new version of the OS may change the system call by saying I add some parameters or I change the arguments. So then an OS, the old version of the OS and the new ones are no longer directly compatible. Any application that ran on the old one may not run exactly the same way. OS virtualization allows you to emulate an older version of the OS using a newer version. So you have compatibility. So the older version will accept older format system calls and still let them run, and you'll do some translation. Okay. That is one use case, okay, where you essentially have something in this OS called Solaris, doesn't exist anymore. Okay. It allowed you to emulate all past versions of your OS. Okay. So you can take any program that was ran on an older OS. You didn't have to port it because you just ran it inside a OS container, which was essentially your OS virtualization, and said inside that container, this will look like some old version of this OS. Okay, even though it's all running on this new kernel. Okay, yes, Kushi. The Windows has something called compatibility mode. Is that the same as OS virtualization? So compatibility mode is typically used for drivers and other applications. It lets you run things that basically don't require new features. It is not using standard virtualization though. It just allows you to pretend like something is an older version of the OS. It has similar characteristics, but it's not strictly virtualization. Okay? Because virtualization requires you to do other things like isolation as well. Okay? So the modern view of OS virtualization is not to run this legacy things. It allows you to essentially take and sandbox application. Okay? You can take an application, you can run it inside a lightweight virtual machine. What that means is you will give it certain amount of resources. Okay? So it runs inside a container, sandbox container. You can also limit what resources it can access and so on. So it's a way to sandbox how applications run and isolate them from one another. Okay? When you sandbox something, so you cannot see anything outside that container and so on. Okay? Now, as far as the process is concerned, it's still, to it, it looks like it's running on a standard OS. Okay? It doesn't see anything different. Okay? And it will, only thing is it cannot access certain things. It might have less resources than if it did not run inside an OS virtualization container. Okay? So here is the picture you want to keep in mind. Okay? So this is OS virtualization. You have hardware. Okay? On that hardware, you are going to boot a kernel. Okay? This is your host operating system. Okay? Now, on this host operating system, you are going to create a lightweight virtual machine like before. Okay? But inside that lightweight virtual machine, you are directly going to run applications. You are not booting another OS in there. Okay? If this was native virtualization, inside the VM, you are going to boot an OS because that is an emulation of an entire physical machine. Okay? Here, it's not an emulation. It is just a resource container that allows this application to run, but you can limit what it can see. So these applications in this container, you can say they don't actually cannot see those other applications. Normally, when you run a process, okay, you start an application, or everything else that is running is visible to it. It can see what other processes are running. It can see all the files on the disk and so on. Okay? When you run something inside a container, you can limit what it sees, how much resources it consumes, and so on. Okay? Now, the reason this is lightweight is there's only one OS in OS virtualization. That is the host OS. There's no concept of running additional OSs inside virtual machines. You can run applications, but those applications still use the same host OS as any other application. Okay? So only one OS, because you're just emulating the OS interface with another OS interface. There's no second OS in this case. Okay? Here's a question, yes. So the question is, can we say that the host OS is a modified OS? So the host OS has support for containerization, okay, which means that you can basically create these sandboxes. But other than that, you don't need to modify it any other. It just needs to support this concept of OS virtualization. Question. So question is, what other use cases do we have? Basically, with that, when we get to Docker, you will see that there are all kinds of use cases, because Docker is essentially going to use containers. Okay? It allows you to deploy portable applications or all kinds of things you can do with this. Okay? But our basic use case at this point is we can isolate applications from one another. If this application does something malicious, it cannot actually attack something else because it cannot even see those applications. Normally, one application can go and essentially do something to another application because they all run in the same on OS and they can see one another. Okay? You can limit what files the container application can see and say that these directories are not visible. Okay? So when it actually looks in the file system, some directories become invisible. So you can protect sensitive files. You can do all kinds of things with this. Okay? So here is our example of type 1 virtualization, type 2 virtualization, and OS virtualization. So this gives you a good example of how they are different. Okay? So in type 1, you have hardware. Okay? The hypervisor is the OS. It booted on the hardware. Okay? You created 2 virtual machines. Inside each virtual machine, you booted a second operating system, which is your guest operating system, and then you ran applications. Okay? So there is no host OS. There's only type 1 hypervisor, which is the OS, and there are guest operating systems. This is type 2. Okay? In type 2, you have hardware. You boot a standard OS, Windows, Linux, Mac, that is your host. Okay? Then you start the hypervisor. That's a standard application in this case. Okay? And that application allows you to construct virtual machines, same as before. Inside each of these virtual machine, that's a full emulation of a physical machine. So you boot a OS, and on that OS you run applications. Okay? So there are 3 layers here. There is a guest operating system, the hypervisor, host operating system. Okay? That is OS virtualization. Okay? You just boot an OS. You create a lightweight virtual machine. Okay? But this virtual machine is not an emulation of a physical machine. It essentially exposes some limited resources that are already present on this machine. And you just have applications in them. There's no OS inside these containers. Right? There's no special hypervisors or anything like that because it's only an OS. Okay? And the OS is virtualizing itself, letting applications run inside sandboxes. Okay? So it should be clear that containers are much more lightweight. To start a container, you don't have to boot another OS, which you would have to do here. And you can create them very quickly and just start a process in them. Okay? Here you have to actually create a VM, boot the OS, then run an application. So it's a much more heavyweight construct. And I know containers are much more lightweight as a result. Is this clear? Okay. So there are 2 things to keep in mind as to how you are going to implement an OS container, especially in the Linux world. Okay, LXC is Linux container. Okay. So I'm just going to give you the Linux use case. Other operating systems do somewhat similar things. Okay. There are many concepts, but we'll focus on 2. One is called Linux namespaces. Another is called Linux C groups. Okay. Namespaces allow you to control what a container can see. What resources can it see? Okay. C groups can allow you to control how much resources you consume. Okay. And let me give you an example of both. Okay. But there are other things you will do as well. You can use something called change root and prevent that container from seeing certain files altogether. Okay. That allows you to control which files are accessible, what becomes a root directory, and so on. There are additional security modules we are going to ignore. And there are additional tools like Docker, which we'll get to, that allow you to manage containers. They're not adding anything to containers themselves, but it's an easy way to manage applications that are containerized. Okay, so let's talk about namespaces. So what does this? A namespace is a Linux concept that restricts what a container can see. Okay? So what can you restrict? Okay? You can restrict which process one process can see. You can say this process can only see process number. Processes are numbered. You can say this process can only see process 10 and 15, but none of the other processes. Okay? So once you put it in the container, even though there may be lots of other processes running, when that process does something like PS or top or anything that allows you to see processes on the system, you will see a subset of the processes that are allowed to see and nothing else. Okay? So you can limit, you can provide the first, you can provide the illusion it's the only process. If you say you'd see nothing else, okay, and it looks like you are the only process running in the system, because you actually all the other processes are hidden from you. But you can also control which other processes you can see. Okay? Then you can control mount points on which files you can see. Okay? You can say only these files, but not these other files. So although all the files are present on disk, inside the container, you can only see some subset of the question. Yes. Yes. Question is, can you allow a process inside a container to see what is outside the container? So the container is the subset of what you can actually see in this case. So process IDs, what process IDs are visible. Once you create that subset, all processes can see each other in that group. Okay, so that becomes your container. It's not like you're seeing something outside. The container is defined by what you can see. Okay? You can also limit which users on the machine are visible. So you can say there may be 10 users with logins, but inside this container, only one user is valid. All other users are not even valid. So they cannot actually, you inside that, you will not even see those other users. You can't log into that. There's no concept of logging in, but that container will not allow you to essentially other users to access it and so on. Right? So you can control all kinds of things as to what is accessible and what is not accessible. Okay, that is namespaces. Okay. Now a related concept is called C groups. C groups are now going to allow you to control how much resources you consume, not what you can see, but what you can consume. So here you can control how much memory is allocated to a container. So this container gets 1 GB of RAM. That other container gets half a GB, right? So any processes that are running in there, if they start taking more memory, the OS will terminate it because it does not have access to more than the allocated amount. Okay? You can also control how much CPU you can get. You can say this container has access to 1 core and core number 1. Okay? In that case, the CPU scheduler will take that process and only run it on that core, because that is what you limited it. Okay? And then you can say this other container gets half a core. Okay? That means not only is it going to run on that core, it will basically get half the CPU. Okay? You will basically limit how much CPU it can consume. Okay? So you can control memory, you can control essentially how much CPU you get, you can control how much IO you can perform, you can also control how much network bandwidth you can use. Okay? You can say this container can only use 100 megabits of my 1 gig Ethernet card. So no matter how much traffic you are trying to send, you will be limited to that quantity. You will not be able to send more, even if the resource is not being used, because that's how you control its resource usage. Right? So all of that is done through this concept called C groups. C group means container groups. Okay? So when you create a C group, you have to specify what resources are actually going to be used by that group and how to limit it. Okay? And there are concepts like you can, of course, create more than one container and then split the resources across them. Right? So we'll talk about this notion of proportional share scheduling that allow you to control how much CPU resources you can get. You can do the same thing with network resources as well. Okay, I'm going to talk about that in a minute, but are there any questions on namespaces or C groups? Okay. Namespaces allow you to limit what you can see on the system. C groups allow you to limit how much resources you can use on the system. Okay. When you put these two together, you essentially have Linux containers. It's a way to isolate application, okay, and basically allow it to consume some subset of the resources. Okay, so effectively a sandbox your application by limiting what it can see and how much you can use. No question. The question is, once you have created a container and you have allocated some resources, can you change those resources? So there are standard utilities that allow you to change all of that on the fly. Okay, so you can say, I gave this 2 GB of RAM, I'll give it more. Or I gave it 1 core, I can assign 2 cores. So all of that you can do on the fly. The OS will just change that allocation and you'll have more or less resources. Okay, that's very easy to do, very lightweight. Okay, all right. So this I'm going to skip because we talked about all this. Talk about proportional share scheduling. I'll just introduce the concept. We have 1 minute left, and then we'll come back to this next time. So what is proportional share scheduling? This is a way by which you can take some resource on your machine and partition it or slice it across application. Okay? You can say this process gets 30% of the CPU, that other process gets 20% of the CPU, and then the CPU scheduler will ensure that it gets only that share and never more. Okay? In a standard machine, there is no control, right? You start a process, okay, it can create threads and take as much resources as it wants, right? So you can essentially hog the CPU by creating lots of threads or having lots of computation. If you want to limit how much you can consume, you use what is called proportional share. So you give it a share. Okay? Now the share typically is specified in terms of a weight, which is a number. Okay? So essentially you give a weight or a numeric value to a process, and that weight dictates how much you can get. Okay? So if you have two processes, each of them gets weight 1, you share the resource, in this case CPU, in the proportion 1:1. Okay? So 1:1 means equal share. That means each of them gets 50%. Okay? If you have 3 processes, okay, and you give them weights of 1, you'll have 1:1:1, which means you get a third. Or you can say this process is a weight of 1, this other process is a weight of 2. Okay? So this gets 1/3 and that gets 2/3 because you're splitting the resource 1:2. Okay? So you can give weights and you'll get allocations in proportion to your weight. Okay? And how we do this, we'll talk about next time. But that's the basic concept. So when you construct the C group, one way is you can give each container a weight. Okay? And its CPU share will be in proportion to its weight. Okay? Another way to do it is you can actually give it physical allocation, saying this container gets core 1. Okay? That's not proportional share, that's actual allocation. Okay? Then it can only run on that core. There are many ways to do this, but proportional share scheduling is a flexible way. By giving this very simple concept of a weight, you can control how much resources you. Okay? So next time we'll see how to do this. So today we are going to stop here. Right?